distribution character of pi which was a distribution on compactly supported functions on G. So in the dual of compactly supported functions, the usual setting for distributions. And question?
Is admissible essentially necessary? I mean, there's no way to define a trace for other ones?
I don't know how general you can make this. I would imagine that you can't make it very general beyond this setting. These
No, I mean, yeah, I think admissible is the only reasonable assumption.
Yeah, so maybe in some very special cases you can push it further, but this seems to be, as Dragon says, the only reasonable thing. Okay, so what did we want from this? Well, we wanted to maybe recover the familiar properties of characters that we had in, say, the case of finite groups. So let me just call it on. So the zeroth property is that theta pi d is invariant. So that is theta pi d applied to the function I get by translating on the left and then translating by the right on x is the same as theta pi d of f. Okay, so that's like saying that the trace of a finite dimensional representation is conjugation invariant. This is easy to verify from the linear algebra properties of the trace on finite rank operators. So if you want to prove this, you go back to the definition we gave in terms of traces of these finite rank operators, and you just verify that the trace there has the right property that when you conjugate by a matrix, you get the same answer. The other property is that if pi 1 and pi 2 are irreducible admissible representations whose GK modules are inequivalent. So that is to say, that are infinitesimally inequivalent. Then the characters are independent. So this is wonderful. We can tell apart, we can tell infinitesimal equivalence classes of irreducible admissible representations apart by passing to distribution character. And it's additive on short exact sequences. That's another thing that just follows from the formal properties of traces of finite rank operators. So
I mean, this one, to make sense out of this, you should have finite family.
this,
No. When you talk about
one.
independence, here you should just say the different person. Like if you really.
Okay, so I think what you want me to do is put k of these here, or maybe L of these are linearly independent. Okay, yeah, that's a better way to say it. Okay, so, or the correct way to say it. And then if 0 goes to u vw is an exact sequence of admissible representations, then the character is additive. The distribution character of the middle representation is the sum. Okay, so as I said, 0 and 2 are elementary properties of the trace as we defined it. 1, you have to do a little something, which I'm not going to do. Okay, so at least it does the right things for us. Okay, so So I think what I'm going to do is I'm going to state some general theorems about characters in general, and then do a couple examples of computations. And there are more computations on the back of the reference guide, so we'll come to those momentarily, or in the second use of momentarily. Okay, so here's the main theorem on characters. And it's sort of stated in sort of a backwards way. So the first is that there exists a locally integrable function theta pi, so fix pi miscible representation of G. And then there's a function that's integrable on any compact subset of G, such that the distribution character of pi evaluated f is simply integration against. Question?
Is it obvious that an admissible representation has finite length?
No.
Only for irreducible representations is it an eigendistribution, and then you get the fact that it is locally L1. So if it is a finite length, then it is still locally L1. But if it is not, I don't see.
Okay, so
Just assume that all
yeah,
everything is finite length, right?
yeah. So that's right. So yeah, you're right. So basically, as we'll see, to prove theorems of this nature, we'll want to study the character as some sort of eigendistribution, and you would like to know that z of g acts locally finitely on it. So you need some additional assumption. That's right. It just has a finite composition series. So the composition series just has a finite number of elements in it, finite number of representations. So if you want, just assume pi is irreducible admissible. That's fine too. So there's that. So remember, a source of distributions is integrating up against functions. Certainly there are more distributions than functions, but this theorem says that this particular distribution is given by a function. Okay? And then sort of the precursor to proving this, so this is kind of backwards, but I'll state it this way. So this function restricted to the so-called regular set, this is defined to be the regular set, which in the case of SL2 is the set of x in SL2 such that the trace of x is not equal to 2. So you don't want the eigenvalue 1 to repeat itself. You don't want it to repeat itself twice. Okay, so this is analytic. So what this means is that if I have a function of compact support whose support is contained in the regular set, then it's the distribution character applied to that function is the integral of a real analytic function up against the function you started with. So i.e., if f is compactly supported and smooth on the regular set, then the distribution character applied to f is the integral over g of some analytic function. Well, I'll write it this way. From 1, we know we can write it. And the point is that this is analytic. The restriction of this function to the regular set is analytic. Okay. So, well, f is supported in G prime. So if you want, you can integrate over G prime. Let's just leave it as G. Okay, so those are the two main theorems. So on the regular set, the character is given by integrating up against an analytic function. And there is nothing, the singular set can't contribute anything to the distribution character. So if you only knew 2, 2 does not imply 1, of course. If you knew 2, the whole distribution character might be some sort of Dirac delta function on the singular set, evaluate the singular set, and then add the contribution to the regular set. But that doesn't happen. Regular set determines everything. So in terms of depth, 1 is a much more difficult result than 2. So I think we had planned at some point to sketch a proof of 1 that works in general, but I think we've abandoned that. So we're not going to prove, this is so-called Harshanda regularity theorem. You prove that this distribution character is given by a locally L1 function. Okay. So what is the tool to studying this? And as Rishi says, it's studying families of differential equations, or one differential equation in the case of SL2. So, well, the main tool to establish at least 2 to begin with, it follows, is well, I'll say the theorem in general, is the following computation. So let omega be in the center of G. This is the Casimir element. Okay. Then the main point is that if I take a function of compact support, apply the differential operator, apply omega acting as, say, left invariant differential operators on F, then apply the distribution character of pi to this, I get, so let me, so I'm going to, so assume omega acts by lambda, the scalar, on this representation H. So, so my hypothesis is slightly different than this. I'm fixing an admissible representation on which the scalar, on which the center acts by a scalar. So for instance, again, I could take H to be irreducible. Okay, then the main computation is that if I have a function of compact support, I act on it, and I apply the distribution character of pi, I end up with lambda times what I would have gotten had I applied the character to F. Okay, so let me rewrite this in several different ways, and then I'll just sort of sketch why this is true. At least it seems very plausible. If omega acts by a scalar in the representation, then it acts in this, that scalar action persists in an equation of this form. So a better way to write this, and Castleman discussed about how to differentiate distributions by using the transpose of differentiation on functions. So it's better to write this as omega. So this is an equation of distributions. Okay. So this is a quality of distributions. And this is simply, if you want, a translation of this equation, to different terminology. This is what it means to differentiate distributions, or act by a differential operator on distribution. You act by the transpose map. Okay. So let's see why. So maybe I'll make a definition. So any conjugation invariant distribution on G that satisfies star satisfies this equation is called an invariant eigendistribution. Okay, so conjugation invariant is this property 0, and the other quality of being an eigendistribution is that you have to be an eigendistribution for this the action of the center. Okay, so just as an exercise in terminology, the distribution character of an irreducible admissible representation is an invariant eigendistribution. So let's see. So this is dangerous, but let's just do a little schematic or sketch of this property. So we want to look at pi of omega of f and relate it to pi of f so that after we take the trace of these two operators in the appropriate sense that we defined last time, they differ just by lambda. So if we could show this is the case, then after taking traces, we would get this. Okay? So we just want to examine how the left-hand side relates to the right-hand side. So the left-hand side is, so the left-hand side is this operator, integral over g, omega f of g, pi of g, dv. So let's examine it by looking at a particular matrix coefficient of this operator. So we fix, this should be dg. So fix v and w in h. So we have the integral over g. So a coefficient is the VW coefficient is omega f g pi of g v inner product with w g. Okay, and so here's the scheme. If omega, say, were a first order operator, we were just differentiating once, then by integration by parts, we could move that over to pi of g and pull it out this way. So this is some sort of, as I said, this is just a schematic. So use integration by parts repeatedly. I mean, omega is not a first order operator. You have to do it twice. Move everything over there. But now you've got omega sitting here. Now it's central. So I can move it past the pi of g. Okay. And so now I've succeeded in moving this omega by this composition of integration by parts and the fact that it's central to up against v. But it acts by lambda on v. So this is lambda times, it's lambda times the VW coefficient for so this is the VW coefficient, lambda times the VW coefficient of pi g. So that establishes that this equality, and then after taking traces, we get this equality. So that's just a schematic, how that works. Okay, so this is a translation of, this is the same. This is the definition of what it means to take omega and act on a distribution. Prove this or prove this. I mean, these are. I mean, this. When I say better, this is just notationally better. Say. Notationally better formulation of this property. Okay. The boundary term disappears because one of these things has f has compact support. So yeah, so that's right. So that came up somewhere in Castleman's lecture. When you do integration by parts, you know that there's the switch, there's the switcheroo, and then there's a boundary term. But if you're integrating something with compact support, the boundary term goes away. That's another reason to take things with compact support. Well, yeah. I mean, if the limit is 0 on the boundary, then it goes away too. But, so. Okay. All right. So one scheme is if you want to study characters of irreducible representations, you just study this differential equation. Study invariant eigendistributions, see what you can say about them. Let's write down our first example of distribution character. So, and then we'll see how the general features of this computation abstract and generalize. So, example I want to consider is if FD is d-dimensional representation of SL2. Okay, we'll let theta b be its, oops, no, k-dimensional. We want to compute its, well, I think since D was in my notes, if I do change now, I'll be in trouble. So compute trace of pi of g on FD. So now there's nothing to do. It's finite dimensional. You don't have to worry about anything. You can just take the trace. And so G is either conjugate to so let's compute the trace where G is in the, well, G is conjugate to one of three things of this flavor. So there's e to the t, 0, e to the minus t, and that you could have plus or minus that. You could have cosine theta, sine theta, minus sine theta, cosine theta. These are the things that form the regular set. The singular set consists of the things with eigenvalue, with the eigenvalue 1 appearing with, or minus 1 appearing with multiplicity greater than 1. And so this would be, so epsilon is plus or minus 1 or 0. Okay, so this is the regular set. And this is the trace 2 set. This is the singular set. Okay, so we could just write this down. This is not rocket science, so we just, so FD is the span of y to the d minus 1, x to the y to the d minus 2, and all the way up to x to the d minus 1. So let's just compute the trace of the things that are conjugate to, say, this hyperbolic element. Okay? So we have to see how this acts on each of these. Of course, this is an eigenbasis for the action of this element. Y to the d, I pick up a coefficient e to the t times d minus 1. This one, I pick up a coefficient e to the, oh no, this is minus, right? Y is acting by the change of variables. Y goes to e to the minus t times y. So this element, if I put in e to the minus t in for y, pick up this coefficient, so on and so forth. So here I act by e to the t, and then e to the minus t d minus 3, all the way on up to e to the t d minus 1. Did I screw something up?
Maybe not.
Oh, that's a d minus 2. Yeah, sorry. Yeah. I think. Okay. So what do we get here? So we get e. So this is e to the minus t d minus 1, e to the minus t d minus 3. Yeah, sorry, I was getting ahead of myself. So the trace equals this plus e to the t d minus 1. And now we're just going to reorganize this little finite sum in a way that's going to generalize. So this is exactly the reorganization that comes up in the Weil character for finite dimensional representations of compact groups. Weil character formula. So I claim I can write this, well, I can write this as e to the minus t times d minus 1 plus, and I can take it to the end, and then keep going forever and ever. And subtract off the extra terms. Okay, and so let's factor that out. And then I get e to the minus t d minus 1 minus e to the t d plus 1 times 1 plus e to the 2t, c to the 4t. Huh? Yeah, I'm just doing some manipulations here. So I mean, it'll make sense. It'll make sense on this regular set. So. Okay, so what is this? This is e to the minus t d minus. So the formula I'll get in the end will make sense. Okay. I just take the geometric series and write it like that. And then, let's see. Now I want to multiply the top and the bottom by e to the minus t, I think. And so downstairs I get e to the minus t minus e to the t. And upstairs I get e to the minus td minus e to the td. That looks pretty good. And that's the trace of pi of e to the t0. So it has this very simple symmetric form. The exponents that are appearing here, d, is not the highest weight. The highest weight was d minus 1. Instead, it's how the Casimir acts it's the infinitesimal character. D rho is the infinitesimal character of the representation with dimension d. That's one of the entries in this column. Okay, and so now we can also compute, by the same manipulation, the trace of the hyperbolic elements, or elliptic elements rather. Trace of pi of cosine theta, sine theta, minus sine theta, cosine theta. And to do this is, well, just do a little trick. I mean, this is the trace of pi of e to the I theta, e to the minus I theta. Of course, that doesn't live in SL2R, but these representations are actually representations of SL2C, so I can conjugate there, compute the trace, and that's what I'll do, because once I do that, that's the same calculation that I did here, except where I see a t, I put an I theta, and so this equals e to the minus I theta d minus e to the plus I theta d divided by e to the minus I theta minus e to the I theta. And of course, all these, I mean, these are just sines or cosines. They cancel out, so this is a real number, even though it looks like a complex number. Okay, so in either case, the formula for the character of a finite dimensional representation on the regular set is very simple. There's this denominator term, and there's some numerator. The numerator involves this number that's appearing in the parameterization of the action of the center after applying this Harish-Chandra homomorphism. After applying the row shift, this looks very symmetric, these exponents. And the miracle is that when you write down the differential equation corresponding to a general eigendistribution, you solve it, you get the exact same kind of formulas. So let me write down a general theorem about what solutions to that system of differential equations look like, what invariant eigendistributions look like on the regular set. Exactly. So of course, this isn't defined on the singular set, right? That's where the denominators are 0. But this is an analytic function, and the content is that the singular set doesn't contribute everything. So this contains all the information. Okay, so here's the theorem of Harish-Chandra. So suppose, let's see, chi is an invariant eigendistribution on G. Well, maybe I'll call it theta, actually. Suppose theta is for which the center acting on theta is chi sub lambda of z theta. Okay, so before I had written down what it meant for it to be an invariant eigendistribution for SL2. So that meant omega acted by this, well, maybe I shouldn't call this lambda, maybe I should call this nu. Because, so what's the relationship between this? So this chi sub nu, so here, nu is an H star, okay? So evaluating at H star corresponds to not evaluating the Casimir at the same value, but this would say in SL2 that equals nu minus 1 theta, I think. No, I think it's nu squared minus 1 over 4, actually. Yeah, I think that's right. Remember, we went from the action of the Casimir, we did the computation of what the Hardy-Chandra isomorphism was explicitly, and if the Casimir acts like this, then the element H and H star acts by nu, okay? So just writing this in slightly, this will make life more symmetric, okay? Because the powers that appeared here weren't d squared minus 1 over 4, they were d. So, okay. So fix a Cartan. H, so in case of SL2, that's either K or MA. Okay. Let H prime denote the regular set. No, so this is a Cartan subgroup, Cartan subgroup H of G. Okay, so it's either the circle or the diagonal in the case of SL2. Let SL2, H prime denote the regular set in H. So those are the ones, so the eigenvalue of 1 doesn't appear too many times. In the case of SL2, it's the ones, so the absolute value of the trace isn't equal to 2. Okay. Then, then for x in this, well, let me see. Then we can write theta. Okay, so let's assume this lands in H prime. So we fix some x down in the Lie algebra that exponentiates to the regular set. Then this equals a quotient, just like we saw over there. The numerator is a sum over the Weil group of H and G. So again, in SL2, that either has 0 elements or 2 elements. No, sorry. It always has 2 elements. And what you put here are some polynomials. Yeah. So I've got the E on this side. So I guess I just put. They're always constant, yeah. For characters, they're always constant. And then there's this denominator, which is the determinant of the adjoint action of this xtx on G mod H minus the identity. And then I need to put in here E to the nu to the W nu. Let me see how I write it down here. It's confusing me. Yeah, so maybe W nu of H. Okay. So this is the general form. So okay, yeah, so this appeared in Bill's first lecture. So for SL2, SL2R, there's two possibilities, h equals k, and then the denominator is the absolute value of e to the t minus e to the minus t. Okay, and if h equals is a or ma, then oh no, sorry, that's ma. And if h equals k, it's e to the I theta minus e to the minus I theta. Oh yeah, this would be x. Yeah, sorry. Yeah.
I think you're confusing now, and you can just write these two formulas that replace d by corresponding infinitesimal
Yeah.
character
Yeah. So
with some arbitrary coefficients.
yeah. So for SL2, the general possibility is, so this was the case of the finite dimensional representation in which this nu equals d. The way it looks is it looks like, well, some coefficient a plus e to the minus I theta nu and minus a minus e to the minus I theta nu and e to the minus I theta minus e to the I theta. So this is the general new eigen. So if I have an eigendistribution where the constant is nu, then this is what it looks like. That just generalizes this. I mean, that's the most general form of an eigendistribution where it is nu. If nu equals d, a particular example of such an eigendistribution is the character of a finite dimensional representation with dimension d. And we already saw that where this formula comes from. The same thing here, the most general. So that's a formula on things that are conjugate to cosine theta, sine theta, that aren't equal to plus or minus the identity. Also over here, the same formula holds. The most general thing has the denominator, and the numerator, well, you change d to nu. That's keeping track of the action of the center. And I can put an arbitrary coefficient here and an arbitrary coefficient here. So that's the most general form of these things. So, g mod h. So I look at the quotient of g by the Cartan h. I think that's right.
This is not literally true, right? Because theta is you're taken to be an invariant eigendistribution, not just a character. The
Right. So yeah. So maybe I will. If I take theta to be an arbitrary invariant eigendistribution, then this is a polynomial. If it's a character of a representation, these are constants. Okay. So these are polynomials in general. And they're constants if theta is theta pi. Okay. So yeah, so maybe it was just too confusing. So I should have just maybe concentrated on the formulas that we have. So this is the most general form of a character for SL2, and this on the set conjugate to cosine theta, sine theta. This is the most general formula on the set of elements conjugate to the diagonal.
There's one of these exponents has
Yeah.
plus sign.
Yeah. Sorry. This was a plus up here. It's a plus down. They're not both minus. Yeah.
So I guess I'm maybe getting a little lost in all the notation. So this
Okay.
is hyperbolic sine of TD over hyperbolic sine of T. This is sine of d theta
Yeah.
over sine of theta. So
Exactly.
geometrically, is there some geometry there for the simple case that I should be able to see?
I don't know. Maybe there is. I mean, it's just, what are we doing? We're just computing the trace of this element by change of variables on homogeneous polynomials in two variables of degree d minus 1. And then what you get is you get this quotient of hyperbolic sines or cosines, whatever. I think sines or whatever. And then if you change variables by this and such polynomials, this is the trace.
You could say it geometrically because you're taking the Fourier transform of orbital measures.
Okay.
So that's not a proof, but that could be a geometrical interpretation of.
So what is it? You're taking the Fourier transform of what?
So of every theta corresponding to its lambda, you have a certain orbit, coadjoint orbit.
Oh, okay.
adjoint
Yeah,
orbit,
okay.
And you're taking the orbital measure and taking the Fourier transform of that
Okay.
to get the character.
Okay, that's some sort of heuristic, which we're not really, we haven't discussed yet.
Maybe partially was wondering, I was a little unclear on how you used the x and y's earlier, but you used them for the different things here. So like here, the determinant of doing an x kind of y thing looks kind of like x, y equals 1, which is the hyperbole. I'm just wondering if there's a geometric.
I don't know. I don't know any. These formulas appear for me, just by taking the trace after change of variables. I'm sure there's a beautiful way of seeing why these numbers come out, but I don't see it immediately. So anyway, but the point is not to say that they're hyperbolic sines or cosines or whatever the case may be. It's just the form of the solution. So there's some denominator which always appears, and there's some numerator which is linear combinations of these exponents, and the exponent contains this parameter, which is the action of the center that's governing the system of differential equations. Okay, so it's the form that matters more than the details. It's this form or that form, or more generally this form. And the point of all this is that in this situation, when you do the solution, you find that naturally that these polynomials can't be, well, in the case of characters, for instance, you find that these are constants. Okay? So what is the dimension of the space of possible solutions? Well, it's finite dimensional. So that means, so as a corollary of all this, that is to say that the space of invariant eigendistributions with the fixed action of the center is finite dimensional. So as a corollary, and this, I'll explain what, well, there exists a finite number of irreducible admissible representations with fixed action of the center of G. If I fix nu, space of invariant eigendistributions for that parameter nu is finite. So there are a finite number of them. So Dragon would say, and he would rightly say, that this is the first proof of this fact, but the most transparent proof comes from D modules, so he's going to give that when he talks about D modules too. This number, this fixed number, is bounded by the number of k-equivariant irreducible local systems on the flag variety or something like that. So there is a geometric interpretation of this number, or at least, well, sometimes that upper bound is achieved, and sometimes it isn't.
Can you give the general definition of this regular set?
Yeah, so the regular set consists of, well, for a linear group, say, consists of elements where the eigenvalue 1 appear.
Then different eigenvalues should appear.
Huh?
All the eigenvalues should be different.
No, it's the eigenvalue 1 isn't allowed to appear more than the rank of the group. Maybe. Okay. So certainly if all the eigenvalues are different, then that's regular. Question?
How do we know that the character determines the representation?
How do we know the character determines the representation? Well, that's when I said that if they're linearly independent. So if I have two different representations, they have different characters. I guess what I omitted saying is if two representations are infinitesimally equivalent, they have the same character. So then this exactly separates infinitesimal equivalence classes of representation. So it is this linear independence which I didn't prove.
Sorry, maybe I missed something. Back to this question for a second. Earlier, we had a matrix with diagonal entries 3 and -1. It wouldn't have been regular.
3 and -1 is not regular?
Not by your definition, because you said anything.
Wait. But that does 3 and minus 1/3, or 3 and plus 1/3?
We were only looking at stuff in A at the time.
Determinant one.
No, that's the A part. So that's not regular.
So I want determinant 1. So this is an A, and this is regular. So
I mean, you could have had 3, and then lower diagonal negative 1, and then
and then 1/3? But wait, but if you,
I was trying to fix the trace to be 2. You're saying the trace can never be 2 except
so we wrote down all conjugacy classes of matrices. So the ones with trace 2 are exactly plus or minus.
it was already diagonal. Okay.
So some of these have trace minus 2.
Or trace, absolute value of the trace is 2.
So this, in terms of eigenvalues, that means that absolute value 1 cannot appear more than the rank of R.
Yeah. So I guess there's two generalizations of regularity. One, you could say distinct eigenvalues are always distinct, and then another one you could say that 1 doesn't appear more than the rank of the group. Here this is rank 1, so 1 doesn't appear more than the rank. Something.
That's minus 1. I mean,
Or minus.
I mean, if one appears very few times but many eigenvalues are the same, then you would still consider it to be regular.
Okay, so let's.
One of the definitions
Okay.
But here you just want to throw away plus and minus 1 in nilpotent.
Yeah. That's what I'm saying.
Yeah,
Yeah, in SL2, I think everyone's clear.
yeah.
Yeah. I think the question is, what is the general definition of regular? Does it mean distinct eigenvalues, or does it mean that one doesn't appear very often, that a single eigenvalue doesn't appear with multiple? Okay, so in that case, okay, so
So this regular and semi-simple and
Yeah, and Harishchandra's definition is what Kostan calls regular semi-simple.
okay,
This is what is going on.
okay, okay. So as you say, distinct so I retract distinct eigenvalues.
Distinct eigenvalues and diagonalized.
Yeah, yeah.
And Kostan's
Well, yeah. Diagonal, semi-simple, regular semi-simple. So diagonalizable with distinct eigenvalues. Yeah. That sounds better. Okay, so now you can flip to the back side of this, and you can look at the formulas for the others. So I didn't write down the characters of the finite dimensional representations. Those are the ones we wrote down. I wrote down the characters of the principal series. Does anyone need one of these? So, this one for you. Anybody else? Anybody else? So I wrote down the characters of the principal series. They vanish on the elliptic elements. They're this expression on the hyperbolic elements. Then the formulas for the sums of the discrete series follow from the formulas for the principal series, together with characters of the finite dimensionals. Because if you believe these composition series, which we've been over several times, that says the principal series is equal, after semi-simplification, to the sum of the discrete series and the finite dimensional. It says the character of the principal series is the sum of the characters of the two discrete series with the finite dimensional. So once you know the finite dimensional, you know the principal series, then you know the sums of the discrete series. And then separating out the individual discrete series, that's a separate matter. Okay, so that we haven't discussed. So, but that's a little bit more subtle. Anyway, you have the formulas. So when you laminate this and put it in your wallet, you'll have those too. So. Okay, so stop there. Question?
I just have one question to make sure I understand philosophically what we're doing.
Okay.
Philosophers over
So what we did, we started with a function from the space of CC infinity function
Yeah.
to C, and from there we said that that's really integration against some other function. And what we're saying is that this function here that we're calling the character is the function that we integrate against to get our distribution.
Yeah, so I think what you said was correct, but there's maybe a few words missing in the middle. So we have this representation of pi. Pi takes G to bounded linear invertible operators on a Hilbert space, H, say. Then from this, we build a representation of this convolution algebra, CC infinity G K. So this is so what is that? So that is, we build a module for this algebra. Just like in the case of finite groups, when you start with a representation, you build a module for some group algebra. This is the replacement for the group algebra. So why don't I call it a module, just to emphasize that. And here, if I take f in this group algebra, and v in a vector in my Hilbert space, then so to define a module, I have to tell you what f times v is. And so now f times v is what we were calling pi of fv, which is the integral over g of f of g, pi of g, v dv. Now, unlike the case of finite groups, where the trace of the character of this representation, you just sum the trace of this finite dimensional representation, and the trace of this group algebra representation are both equivalent in some sort of trivial way. Here, this is a finite rank operator which has a trace, whereas this is not a finite rank operator. You can't take the trace of the identity. Okay, so this was our main tool to build a theory of characters. Okay, so we can take f goes to the trace of pi of f, okay, extends to a distribution the distribution character of pi, which is in the dual space of CC infinity of G prime. Then, the first theorem I stated here, the theorem of Harish-Chandra that was on this board, is that this distribution is given by integrating over a function. That function is locally L1. It's analytic in the regular set. And this is what it looks like in the regular set. There's some denominator which looks like e to the I theta minus e to the minus I theta, or e to the t minus e to the minus t. The numerators are constant in the case of characters, more generally polynomials in the case of invariant eigendistributions, times certain exponents which are all conjugate to each other by the Weyl group. And that's the story that we developed in 2 hours. Question?
So let me give some real bullshit philosophy here. So
Okay.
I started off one of my lectures by saying the trouble with representations of real groups is that you don't get a representation of the group. You often have to work with the Lie algebra. Even here, when you have a representation of the group, it turns out it's neither the Lie algebra nor the group that you want to act. It's the functions in the thing. So this is, in a sense, replacing functions by new distributions. It's sort of another trick you have to deal with.
Yeah.
It's just there are a number of technical problems that keep arising, and this is a major step we didn't make last week. Last week we took the step from G representations to Lie algebra representations. This week we're taking sort of introducing again the functions on the group and saying somehow we have to deal with those also.
I mean, we're discussing this at lunch. I mean, it seems like there's some conceptual barrier in this step. There's no conceptual barrier in this step. Well, I mean, at least there's perceived conceptual barrier that of going from representations to modules for a group algebra. This is a familiar thing to do for finite groups.
But it
And
is
that's-
like stepping from functions to distributions.
Yeah.
You see it. That's
Yeah, I mean,
that's
this
why it's a conceptual barrier.
it's a conceptual barrier because once you build this module, the trace is no longer a function on the group. It's a distribution on this group algebra. So
Technical problems that just keep hitting.
yeah, so they're not. What did Bill say? None of them are very hard, but there are a lot of them, or something. So. Okay, so anyway, that's a sketch of what characters look like of representations. They have this remarkably simple form, looks like the Weyl character formula. I mean, it's just sums of things in the numerator. If you know the Weyl character for compact groups, sums of things in the numerator, there's denominator. Unlike the Weyl character formula, not everything is conjugate to a fixed cartan, so you have different formulas on different cartans, different pieces of the regular set. And that gives one proof of the finite number of irreducible representations, fixed infinitesimal character, fixed central action. So Dragon will give another proof tomorrow, presumably, or sketch another proof. So we stop here, unless there are other questions. Oh, there's another question.
What constants correspond to characters? What choices of constants correspond to characters?
That I don't know. Is there?
Crystallically visible.
Okay.
I mean, one thing Peter didn't mention, this is a part of Harish-Chandra's theorem, that of course these formulas he was writing down were connected components of the regular set in cartans. And there are various relations how coefficients and various components relate.
Yeah.
And
Yeah.
one can, the coefficients have some representation theoretic meaning, which follows from so-called Osborn conjecture.
Yeah.
So they're basically determined by n homology.
Yeah. So I didn't emphasize that, or I didn't say that properly. So X is supposed to be something that exponentiates into the regular set. So the set of possible X looks like chambers in some hyperplane arrangement. And so different choices of chambers correspond to different coefficients. And these transitions, as Dragon says, have meaning. Another question? So how do you do that? So say you look at this formula. There's a uniform bound on the dimension of these polynomials. They're less than the order of the Weyl group. They're less than 2 in the case of SL2. And so the dimension of the space of all solutions to this differential equation, so the dimension of the space of all invariant eigenfunctions with a fixed nu is finite dimensional. Characters of irreducible representations are linearly independent. So they're Yes. Oh, okay. So the precise statement is that there, in this theorem that I raised, in the corollary that I raised, is that there are only finitely many infinitesimal equivalence classes of irreducible admissible representations of G. Yes, you can have. Yeah, infinitesimal equivalence is what cuts you down to finitely many. We haven't discussed. Yeah, that's the notion of equivalence. Other questions? Then we'll stop. So.